It's the purpose of this video to simplify many of the complex problems which occur in the MIG welding industry today. Today's welder has got many variables that have to be adjusted and balanced. For example, is he using the correct size wire and the right type of wire? Should he be possibly using a flux cord, or should it be a MIG wire? And then what about the voltage and the amperage, the wire speed? This has to be balanced very carefully to get a spatter-free weld. What about the gas? And then technique. These are all questions which require answers. And it's the purpose of this video film to provide simple, no-nonsense, straightforward solutions to these problems. You know, selecting a power source today is a little different from what it was 10 years ago. The range of size of power sources has changed dramatically as we've gone, and particularly in North America, to thinner materials. The amperage output requirements is much less now than what it was 10 years ago. Let's look at some of the features that you might want to consider when you're selecting a power source. Some of the units on the market offer the two slope outputs, a steep slope and a flat slope. What does slope mean exactly? Well, in this particular machine, the steep slope provides control during the short circuit. It doesn't allow the current to be too high each time the wire short circuits. So if you're welding thin metals, having a steep slope output provides a little bit better control. And then when you go to spray transfer, you might possibly want to weld 3/16 half an inch steel. Then you would have the flat slope output. The flat slope output actually allows more current if a wire does short circuit, so that the power source can respond more quickly to the changes during a weld. Now, a lot of machines basically may not have these two outlets on here, but they will have an output which is somewhere in between the steep and the flat. Again, some machines have the inductance. What is inductance? Inductance is beneficial, again, in short circuit applications. It kind of slows the current down each time a short circuit takes place, so we don't have this instantaneous response and surge and explosion. In other words, it's really beneficial for cutting down on spatter, and because the arc is on time a little bit longer, the short circuit welds may be a little bit more fluid and therefore look a little bit better. When you look at a power source today, you can simply look to see that the power cable is attached to the positive side, and that power lead should in actual fact find a connection up on the wire feeder. It's usually connected to the torch block. The easy way is simply just to check that the ground cable is attached to the negative side. I've always remembered it the old simple method that reverse electrode positive stands for the Republican Party, REP, reverse electrode positive.
Applications. If welding up to 3/16 of an inch, a 150 to 200 amp single-phase power source is sufficient. 035 wire is the most practical choice. A 250 to 300 amp power source is practical on metals up to 1/2 inch. This is typically a 3-phase power source. This is ideal for 035 MIG wires and 045 flux cord wires. A practical power source for today's fabricator is a 400 to 450 amp three-phase unit, which has a wide range of applications. Ideal for 035 to 045 MIG wires and 045 to 1/16 flux cord wires.
You know, stops and starts in MIG welding are responsible for about 90% of all the defects that occur. And the greatest influence on stops and starts is how you select your wire feeder. Let's look at some of the main features that should be given consideration in selecting a good wire feed system for MIG welding.
Consider the following features when selecting a wire feeder. The drive motor is the heart of the unit. A permanent magnet motor runs much cooler than a shunt motor. A permanent magnet motor also responds much faster for improved stops and starts. Gas coverage is critical at the weld stops and starts. A practical wire feeder feature would be a pre- and post-gas flow control to ensure gas coverage. Also a gas purge switch to eliminate air from the gun. Burn back control eliminates the need to keep trimming the wire for the correct stick-out length. Correct stick-out ensures minimum spatter at the weld starts. For consistent amperage, a digital wire feed speed readout enables the operator to obtain consistent results. An important safety feature is a cold feed control, which feeds wire through the torch without connecting the current.
You know, selecting a MIG gun can be critical if you're a high production shop. There is so much time lost today in production welding because of the wrong type of nozzle. Maybe somebody should have ordered a heavy-duty nozzle. And what about the contact tip? Is it a short one? Is it a long one? Does it suit the specific application? And of course, the gun itself. Is it designed for the duty cycle in which you weld? Can it take the spray transfer? Is it designed for it? There are many factors which should be given consideration in selecting a gun.
MIG gun selection. With power supplies using less than 200 amps, use a 200 amp gun. With argon mixes using up to 300 amps with less than 60% arc-on time, use an air-cooled 400 amp gun. With argon mixes using up to 400 amps with low arc-on times, use a 600 amp air-cooled gun. When welding with argon mixes above 200 amps at an arc-on time over 60%, a water-cooled gun is recommended. When using argon mixes above 200 amps and an arc-on time over 50%, to extend the nozzle life, use a heavy-duty gas nozzle.
We've talked a lot so far about short-circuiting and spray arc. What is exactly short-circuit and spray transfer? These are two different modes of transfer which really make MIG welding unique. As a matter of fact, no other welding process provides two distinctly different forms of weld metal transfer. Now with the short circuiting, considered a low amperage mode of transfer in which the wire short circuits generally up to about 120 times per second. Then we have the high amperage spray type transfer in which the wire doesn't short circuit and it's generally over 200 amps. Deep penetration, high deposition. So you see we have one mode of transfer short circuiting, ideal for sheet metal applications, and then we have the other mode, spray transfer, ideal for thicker plate, generally over 1/8 or 3 millimeter plate. When we understand how to set the parameters for these two important modes of transfer, then we truly understand the MIG process. You know, with MIG welding, it's really the amps that melt the wire. And we have to get amps out of the power source. Now, the voltage will push the amps out, but the bottom line is we have to have a conductor, something for the amps to travel along. Now, if we have no wire coming out of the gun, then we can't draw amps out of the power source. The faster that the wire is fed through the torch, then the more amperage or current it can draw from the power source. Now you've got to remember that the current actually is fed into the wire just about 1/4 of an inch from the end of the contact tip. So it hasn't got far to travel. The relationship between the voltage and the wire feed speed is critical for attaining optimum quality welds. Understanding the relationship between the wire feed and the amperage for a given diameter wire is also critical if you want to achieve maximum deposition in your welds. Let's look at a traditional wire feeder, and which, by the way, most wire feeders run in a range of 650 to 750 IPM, on average around 700 IPM or 300 millimeters per second. The incremental control on a wire feeder may state 0 to 100 or 0 to 10, but traditionally it's in increments of 10, which means each control on the wire feeder is approximately 70 inches a minute or 30 millimeters per second. Let's look at the relationship again of the wire feed to the amperage to the short circuit requirements as it relates now to an 035 electrode. First of all, we can see that if a wire feed control, if we look at it simply as we would look at a clock, we have from the 12 o'clock position, the 1 o'clock position, we can see that the short circuit range traditionally goes between the 7 o'clock position and the 1 o'clock position on a normal wire feeder, which means it's running around 50 IPM to about 420 IPM. The green marks on the wire feed control here are millimeters per second, and we have, as you can see, 70, 140, 210, 280, 350, 420 IPM. It's inside this wire feed range of 70, 420 IPM that we draw in current around 50, 60 amps to around 200 amps. This amperage range is the range for short circuit welding. So on a simple sketch like this, we can now determine a lot of data for short circuit welding. We can determine the current range, 60 to 200 amps, is traditionally found at the 7 o'clock to 1 o'clock position on a normal wire feeder. If you have a digital wire feeder, then it would be between 70 inches a minute and 420 IPM. We can also see that on this simple chart, the voltage requirements for short circuit welding, 14 volts, to 21 volts. A simple setting is as you turn each incremental control one turn, we go up 1 volt. The 9 o'clock position is 16 volts, the 10 o'clock position is 17 volts, the 11 o'clock position is 18 volts. And what about the thickness that we work with short circuit welding? What about the gauge thickness? Well, the gauge range is around 23 gauge to 10 gauge. The most common gauge that's welded is 16 gauge, which is found at the 10 o'clock position. As you can see, the 10 o'clock position around 140 amps, 17 volts on 16 gauge. In conclusion, on this small parameter chart, we could simply look at short circuit welding as being a process that welds less than 1/8 of an inch. And if you had to weld sheet metal less than 1/16, you could see that you would set below the 10 o'clock position, approximately start off at the 9 o'clock position at 16 volts. If you had to weld material over 1/16, then you would traditionally start at the 11 o'clock position, 18 volts. You know, so far we've talked about the basic requirements for short circuiting. Voltage in around 17, 18, wire feed around the 10, 11 o'clock position, or you could even start it off in the middle, as long as you're in the range. Let's look at some real applications with one objective in mind. We don't want spatter, and we want to do all these applications on one simple setting. Applications like, well, 10 gauge plate, vertical up. Applications like 60 foul material, fillet weld. How about a root pass in a pipe? These are basically short-circuiting applications. Remember, the simple rule is if it's less than 1/8 of an inch, or it requires vertical up or vertical down, or you're welding a gap, you simply think of short-circuiting welding. We go over to the machine. With the voltage, we adjust the voltage to strike an arc on the plate and watch the meter so we've got 17, 18 volts. With the wire feed, we simply set the wire feed in around the 10 or 11 o'clock position. And now let's look at the 1/16th application. Again, we will use the same parameters with the objective of a complete spatter weld, a spatter-free weld. As we examine this 1/16th plate, we look at the weld. We can see again, absolutely there isn't one piece of spatter on the plate. And it's really not so much welding technique as it is simply setting those parameters where they should be. It doesn't matter whether you're welding a pipe or a piece of sheet metal. You're going to use short circuit welding. And in short-circuit welding, particularly on quality work, on code work, and on very thin sheet metals, wire stick-out becomes critical. Notice on this pipe application that the wire stick-out is approximately 3/16 of an inch. By keeping the wire stick-out small like this, I can use the minimum amount of voltage, which on an application like this is usually around 17 or 18 volts. If your wire stick-out, like many operators, is going to be a half an inch long due to the fact that your contact tip is now down inside the nozzle, see we have a half to 5/8 of an inch, you will need at this particular setting an extra volt or two. And having those extra 1 or 2 volts every time the wire short circuits, again, the arc becomes a little less stable. So the critical thing is, on short circuit welding, contact tip about 1/8 of an inch outside the nozzle, and the wire stick out about 3/16 of an inch from the end of the contact tip.
Short circuit wire selection. When welding continuously on sheet metal less than 045, use 030 wire. When welding on sheet metals more than 045, use an 035 wire. If using straight CO2 gas, use a high silicon wire, such as an E70S-6. When welding coated or galvanized steels, avoid the E70S6 wires. High silicon wires promote cracking. Use E70S-3.
When you select a welding gas, for short-circuit welding, there are certain factors that need to be considered. If you're welding on very thin metals, less than, say, 60 thou, then it's wise to use an argon mix which doesn't have a lot of reactive gas in it. What does that mean? Well, the typical mix in the marketplace is 75 argon, 25 CO2. But if you're going to weld on 25, 30 thou materials, or weld along the edge of a sheet metal, then why not use argon with we'll say 2% oxygen? Why does this benefit your application? Well, simply from a point of view that argon oxygen uses less voltage than argon CO2. For example, with argon CO2, you would require 16, 17 volts to keep a stable arc. But when you get into argon oxygen, you can work at 13 and 14 volts. Again, where should you use argon oxygen? On sheet metal, where you want to weld along the edge of a sheet metal, on sheet metal, say less than 40 thou, you will find it extremely beneficial to use 98 argon, 2% oxygen. When you're welding on an application such as this, where it's just over 1/8 of an inch, and you want to put a nice bead without spatter, you obviously need more heat. Using now 75 or 80 argon and 20% CO2 is fine for an application like this. But if you constantly weld in a shop and where you're welding on sheet metals and you never go above 1/16 of an inch, then it's wise to use maybe 8 to 10% CO2. After all, you know, when you're welding sheet metals, the object is not to burn through. And if we can reduce the heat just a little bit by reducing the reactive part of the gas mix, then it makes it a little easier.
short-circuit gas selection. Characteristically, CO2 creates a digging effect, which reduces arc stability. Utilizing CO2, the arc is hotter, influencing burn-through potential on thin metals. With CO2, the volt and amp range is very narrow, which makes it difficult for the welder to obtain optimum arc stability. Using CO2, the spatter level increases with an increase in current. CO2 promotes more surface oxides, which should be removed before painting. The material thickness, joint type, and weld position are the prime factors in considering an optimum gas mixture for short-circuit welding. On metals less than 035, argon oxygen allows the use of lower voltages, which reduces burn-through potential and minimizes damage to coatings on the opposite side of the material. Remember, the thinner the sheet metal, the less heat it requires from the welding gas. These mixtures provide the required level of arc energy with optimum arc stability. For increased arc energy, a slight increase in reactive gas improves penetration and weld fluidity. For root passes vertical down or filler passes vertical up on pipe less than 3/8 of an inch thick, use argon 15 to 25% CO2. This provides penetration and arc stability. If the pipe is thicker than 3/8 of an inch, CO2 is required for the filler pass to provide sufficient sidewall fusion. The most practical gas mix for a plant using bulk would be to set the mix at 15 to 20% CO2.
As we increase the current above the short circuit range, we go into an open arc process, which we call spray transfer. Spray transfer utilizes higher currents and higher voltages than short circuit welding. The current range is traditionally 170 to about 400 amps. The voltage range is 23 to about 37 volts. With spray transfer, we can achieve higher deposition rates. Deposition rates in the range of approximately 19-20 pound an hour can be achieved with an 045 wire. With spray transfer, the penetration is excellent. The application range for spray transfer is 1/8 to almost any thickness. But remember, when utilizing spray transfer, it's a hot process. The radiation is high. You need good protection for not only the hands, but for the neck and for the body. And ensure you use a correct lens for spray transfer. The selection of parameters for spray transfer is relatively simple. Do you remember with the 035 wire where we finished the short circuit welding at the 1 o'clock position, around 200 amps? Well, to get spray and to get into that high deposition process, we have to be over 200 amps. As you can see, therefore, the spray range with an 035 wire is between the 1 o'clock position and between the 3, 4, 5 o'clock position. The current range will be traditionally 230 to about 350 amps. The voltage 30 to 34, a voltage range of 30 to 34. An ideal starting point with an 035 wire on many applications, 1/8, 3/16, a quarter, would be to set the wire feed in the middle of its position, the 3 o'clock position, 560 to 600 IPM or 240 to 250 millimeters per second. You would have about 280 amps and 31 volts. That's an ideal simple starting setting. Now the problem with 035 wires is deposition. As we'll see later on, we're going to be working at relatively high currents but at about 50% less deposition than we'll be achieving with an 045 wire. The ideal wire, therefore, for spray transfer is an 045 wire. As you can see, the wire feed range now is extended from the 10 o'clock position to the 5 o'clock position. The current, we need at least 220 amps, a lower voltage, 25, up to 34 volts. 045 is the most suitable wire, not only because it's a lower cost wire than the 035, but also because of this extended current range and the achieved deposition rates. In the current range of 220 to 450 amps, we can achieve almost up to about 19 pounds per hour. An ideal starting point with the 045 wire would be approximately the 2 o'clock position. You want to be somewhere between 400 and 500 inches a minute. Do you remember with the 035 wire, it was in the range of 5 to 600 inches a minute. The 045 wire in the range of 400 to 500 inches a minute, between the 1 and 2 o'clock position, is again an ideal starting point on 1/4 inch. If you need to go to 3/8 steel, then you would traditionally be again at the 3 o'clock position. Once you open up wide open with an 045, you start to get a turbulence effect on the weld puddle down at the higher end. Most of the welding with 045 is done between the 1 and 4 o'clock position on high deposition work. Can you remember where we set the contact tip for short circuit welding? Slightly outside the nozzle, keep the wire stick out short. Spray transfer is the exact opposite. We should set the contact tip slightly inside the nozzle, maybe about 1/8 of an inch down inside the nozzle. Two reasons for this. One, we need a longer stick out because we no longer short circuit. And the other reason is we want to protect the contact tip from the intense heat. The wire stick out should be 1/2 to 5/8 of an inch in length. When you put the nozzle on, make sure the contact tip is slightly recessed.
Remember, when using spray transfer, the selection of your MIG gun is critical. Use the information previously provided under MIG gun selection earlier in this tape. Improper selection will result in early torch failure and a high nozzle and contact tip failure rate, which will also influence arc stability.
In this highly competitive industry, everybody tries to find a way to save $1. If you use spray transfer on 1/8 to any thickness in the flat and horizontal positions, then you can save some money by selecting an 045 wire instead of an 035 wire. You know, an 035 wire in spray transfer is fed at almost a feed rate of 10 inches a second. Now with an 045 wire, the feed rate would actually be in the range of 6 inches to 8 inches. The slower the feed rate through the system, the less feed problems in general. We can also achieve the same high depositions by just increasing the current. We get very good arc stability, a slightly wider voltage coverage off the larger wire. All the economical sense is there. It costs less, it's better to use. So consider 045 wire for your next spray application. In the fabricating industry, if we can achieve, well, 12 to 15 pounds an hour in terms of deposition rates, then we've truly got a handle on our cost. When we look at a weld such as this 3/8 fillet weld, let's see what we can do with both an 035 and an 045 wire. As you can see with the 035 in the spray transfer range, the actual deposition rate achieved is typically between 5 and 10 pounds an hour. As a matter of fact, you may wish to remember that every time you turn the wire feeder one increment with an 035 electrode, you are going up about 1 pound per hour. 1 pound per hour. Now let's have a look at the 045 wire. The spray range again, we can see the difference now. For each incremental turn on the wire feeder, it's 2 pounds, 8, 10, 12. An ideal starting point, as mentioned previously with an 045 wire, is at the 2 o'clock position, which is 14 pounds an hour. Already you are 50% more than you will attain with an 035 wire. Traditionally, again, we do not go too high with an 045 because of the turbulence, but 14 to 15 pounds an hour is readily attained with an 045. This is the reason the 045 wire should be utilized on all applications over 3/16 of an inch. Many cases of spatter and poor welds, it's quite often just a matter of a fine adjustment on the power source.
Too high a voltage results in a quiet arc sound. The weld will be extremely fluid, producing an uncomfortable amount of heat for the welding operator. Smoke levels will rise as voltage increases. The results of too high an arc voltage are all too obvious. High volts will result in unacceptable undercut. Excessive surface oxides are also usually an indication of too high a voltage. Weld bead width increases as voltage increases, resulting in lower penetration. A longer arc length increases the chances of the weld droplet as it is traveling across the arc cap, picking up contaminants from the atmosphere. A noisy crackling arc sound is the result of low voltage. With low voltage, the wire is driven into the weld, disturbing the puddle, causing spatter. The weld bead will be narrow and convex in shape. Smoke levels will be reduced as the voltage is decreased. Notice the decrease in bead width and resultant increase in spatter.
Let's have a look at a spray transfer. The optimum wire for spray transfer is an 045 wire. The wire feed range is the 10 o'clock position to the 5 o'clock position on your wire feeder. An ideal starting point would be at about the 2 o'clock position. That's about 490 to 500 inches a minute. Provide yourself with about 30 volts. Again, adjust the end of the wire so it's just touching the weld. Using the suggested parameters on this video, spatter-free welds can be achieved every time. There's a lot of welding gases available on the market. Many instances, there's so many that there's a lot of confusion out there. When we look at a gas today, basically all the argon mixes fundamentally will do a good weld, a good quality weld. Therefore, what should we look for in selecting an argon mix?
With CO2, spray transfer is not possible. The large, erratic droplets are caused by an upward, repelling force in the CO2 plasma. The arc is always unstable, producing large amounts of spatter. When the CO2 is mixed with an inert gas such as an argon, the droplet transfer changes. 75% argon plus 25% CO2 still produces erratic, large droplets unless excessive currents and voltages are used. A typical argon mix would have 5 to 20% CO2 for spray transfer. 15 to 20% CO2, in contrast to other argon mixes, provides high arc energy across the width of the weld bead. Note the way the droplets are drawn into the weld puddle, adding to the penetration. 15 to 20% CO2 is an ideal mix for spray transfer on heavy plate over 1/2 inch, which requires optimum penetration with minimum porosity. On plate with poor surface conditions, such as rust or mill scale, CO2 in this range provides improved arc stability. As the CO2 content is reduced, weld droplet size decreases and falls axially. The narrow, stable arc produces central penetration. 5 to 12% CO2 is ideal on 1/8 to 3/8 inch clean plate. 2 to 5% oxygen added to argon produces weld droplet transfer similar to 5 to 12% CO2. The shorter arc length is a result of lower voltage requirements. Penetration is typically finger-shaped. 2 to 5% oxygen is ideal on 1/8 to 3/8 inch clean plate. Argon tri and quad mixes all produce stable droplet transfer, similar to argon oxygen mixes. As the reactive gases or helium content increases, the arc energy will increase proportionally. These mixes are typically used on 1/8 to 3/4 inch moderately clean plate.
This particular plant, or this style of plant, would do well to put its gas at about 15 to 16% CO2. Now it has a gas for short-circuiting. It also has a gas for spray on any application. It also has a mix which is very suitable for flux cord wires, all position type wires. It has a good multi-purpose gas which will get the job done and provide all the energy required for the specific applications. What we've discussed in this training film is really understanding parameters. We don't have to remember the type of amperage for every thickness. We simply have to remember that if we're welding thin metals, that to simply put the wire feed around the 11 o'clock position, or if you have a digital wire feeder, set it up around 150 to 200 inches a minute. And remember to put the voltage for short arc at, well, 17, 18 volts. And if you're welding the very thin metals, then put the voltage at 16 volts. As we go into the thicker materials, we go into spray transfer. And with spray transfer, we simply put the voltage. Now we add another 10 volts to what we had when we were short-circuiting welding. So 27 volts. Put the wire feeder around about the 2 o'clock position. Or again, if you have a digital wire feeder, put it about 400 inches a minute. Then make slight adjustments on the arc. If you see spatter, it usually means the wire is driving into the weld. If you slightly increase your voltage, a gap will be created between the end of the wire and the weld, and we will have less spatter. So you can either slightly increase voltage or slightly reduce the amount of wire that's running into the weld. That's what spatter is. It's the wire running into the weld. We'd like to thank Fruhoff Trailer Company here in Canada for their cooperation in making this training film. And we hope it will be of some benefit to you. Thank you.